In the previous class, we have seen that if we have a glass plate and shine light on it from one side, then approximately 8% of this light is reflected and 92% of the incident light is transmitted. So, in a way, you may think that this glass plate, this is glass, this is the glass plate behaves like a transmitting optic. Although transmission is pretty high, 92% of the incident light, while 8% of the incident light is reflected. So you may obviously wonder if this can be used as a partially transmitting mirror for a laser, because you know a partially transmitting mirror is prerequisite for the operation of a laser to couple part of the light which is stored inside the cavity as a useful loss which forms the laser beam. All right. So let us try to understand this and try to provide an answer to whether this glass plate, which offers by itself 92% transmission and 8% reflection, whether it can perform as an output mirror, it's partially transparent mirror for the operation of a laser. Well, as you already know, that in a laser you have an active medium that is a medium in which you have inverted population between two energy levels. And you place this medium between two mirrors which forms the cavity. One mirror is usually 100% reflective and we make it slightly concave to make the cavity stable, to add stability to the. And the other mirror is, of course, partially transparent mirror. And we would like to know whether this ordinary glass plate, which offers 92% transmission and 8% reflection, can perform as an output mirror of. Now, the gain that has been imparted in this medium, we know that it doesn't occur single frequency. Instead, the gain is spread for multiple frequencies in accordance with Heisenberg's uncertainty principle. Now, the cavity, of course, supports oscillation only on some discrete frequencies or wavelengths, which are called cavity modes. The cavity will have endless number of modes, but we consider only those modes which the frequency of which overlaps the region where the gain exists, gain occurs. So, lasing would occur only on these cavity modes, which can oscillate back and forth inside the cavity without decay. Now, this mirror shows a transmission loss which is 92%. So the loss is quite high. And as this loss is independent of the frequency, the cavity modes, therefore this loss can be represented as a straight line parallel to the frequency axis. And as this loss is 92% loss, pretty high, transmission, 8% reflection. So we show the loss line helic level. This is the loss line. Now, as you know, for oscillation to occur, the net gain mode should have a net gain, meaning it's the gain must exceed the loss. Now you can see for even for the mode which has the highest gain, its gain is less than the loss. So it would not less. But you can of course say that, well, we will pump medium harder and create more population inversion that will result in higher gain, and therefore we can arrive at a condition where the gain has exceeded the loss. Now see, under this condition, you can see this mode is a gain which is more than the loss. And therefore, of course, this mode. But pumping it so hard that gain can be so much higher that even a cavity with 92% loss, 92% lossy cavity, the gain can exceed loss, is not a very simple affair. Maybe for certain laser it could be possible, but in general, this will be a very impractical proposition to increase the gain to such a high. So then, what will be the other option? Other option would be, the other alternative would be to bring this loss line down. So now again, for the same gain, we have brought the loss line down. So the same mode once again would less. In fact, this condition, you see, another mode. This mode also has come loss and its gain. So how do you bring down the loss line? You will have to reduce the loss of the cavity. That means you will have to increase the transmission of the cavity. Typically, the transmission loss generally is kept, say, between 10% to 20% or even less. So that means this glass plate, which offers naturally this kind of transmission reflection, may not be a good candidate to be used to perform as an output coupler. And you must have a method to manufacture such partially transmitting mirrors of varying transmission rate, because different laser may require different level of loss for its optimized performance. And even the same laser under different operating conditions may require different kind of transmittive optics. Therefore, you should be able to manufacture, fabricate transmittive mirror of varying rate. Now, I will tell you here how, with the knowledge that we have acquired in the previous class, while we studied Young's double slit experiment, can be used for this purpose. What we found is that when two rays of light interfere, then the path difference, if the path difference of the two rays of light is 0, sorry, if the path difference, this is the path difference. When the path difference is 0, sorry, excuse me, the path difference is 0 here, and it is lambda by 2, and lambda, and this is 3 lambda, so on. We know this. When the path difference is 0, the two waves, they interfere constructively. Their intensity is reinforced. And when the path difference is lambda by 2, the two rays actually annihilate, the two waves totally out of phase and they annihilate. And for path difference lying in between or in between any bright and dark region, the fringe intensity will vary from 0 to maximum. This, therefore, in other words, says that manipulating the path difference between the two interfering waves, the intensity of light upon their superposition can be varied in a controlled manner. If you vary the path difference, so here from 0 to lambda 2, you can vary the intensity of the light of the interfering beams in a controlled manner. So let's see how do we use this knowledge and get transmitted light of different transmission. All right. So we begin with the glass plate. We would restrict ourselves to the case of glass because it has, as we have seen, it has a transmission window over a very wide spectrum. Therefore, it can be used as an optics material for a number of things. So we begin with glass plate, which of course left to itself, as we have seen, this surface will reflect 4% of the incident. But what we do now, we deposit on this surface a thin film of a dielectric material which is transparent to the wavelength for which we want to operate the laser. We want to make this transmittive optics. Suppose the wavelength is lambda. So this dielectric should transmit lambda. That is the condition. And the refractive index of dielectric also has to be appropriately chosen. Now, I'm not going into detail, but I'm giving you just qualitative idea. Physics, underlying physics. How do we exploit the knowledge that we have acquired to achieve this? So now, the light shines on it. This is air, and this is dielectric material of some refractive index, UD. This is glass. This is where so its refractive index will be, of course, 1. Now, as light shines on it, depending on its refractive index and air's refractive index, we know, according to Snell's law, according to Fresnel's calculation, a fraction of light will be reflected. This is the reflected component. Now, rest of light goes here, transmitted light, and then it interacts, it falls on the interface between glass and then dye. First interface was between air and dye. So from here again, a fraction of light will be reflected. So for glass and air, it is 4%. So for dielectric and the glass, depending on the refractive index, a small percent, maybe 4, 5. We need not calculate it exactly. Some part will be reflected. And then this again falls on this interface, that is dielectric to air interface. And here again, a very tiny part will be reflected because this itself is rather small because it is a reflected component. So the fraction that will be reflected from this will be again very small. So now this actually transmitted part. The interference now will occur between these two rays. The one which has been reflected from this surface and one which has traveled the thickness of this film twice, it has gone, can come back. So the interference between these two. Now suppose we have chosen thickness such that this 2t, that means it has gone and come. So path difference between this and this ray is 2t. Now if we have chosen t in such a way that for this wavelength 2t becomes lambda by 2. That means these two rays will interfere destructively. The two waves, if you see the wave picture, they will annihilate each other. That means one wave, the other waves they will line up, and so they will annihilate. That means nothing will come out. Everything will get in. So in effect, this coating is now behaving as anti-reflection. It doesn't allow any reflection to take place because the thickness is such that these two rays of light is interfering destructively. Because the path difference, if it is odd multiple of lambda by 2, we know a destructive interference occurs. So the entire light will get into the glass. And now it will again shine on this, in this interface, glass to air interface, and then a part of it, that is again that Fresnel reflection, will be reflected and the rest will be transmitted. Now if we want to get rid of this reflection, then what do? We once again deposit this dielectric thin film on this side. And so now you see this light which shines on this part will be reflected from here, and then it goes, and then another part will be reflected, come here. So they will again interfere, and if we make this thickness again such that the double of this, the path difference will be, this ray has traveled this distance twice. Path difference between these two rays will be 2t. I make it again lambda by 2, this path difference. So once again, this light will simply get out without any reflection. So this again would behave like an anti-reflection coating. So I've succeeded in making this glass plate by depositing thin film coating to an anti-reflection coating, that the light which is incident on it, entire light is transmitted. There is no reflection, 100 transmission. Such glass plate with anti-reflection coating on either side is very popular, wide use in various laser systems as window. For example, let us think that we have operating a gas laser. So we have to put the medium in a closer in a cell. You have to put your gas. Normally, the operating pressure is less than the pressure. It could be even more than that. But nevertheless, the two ends of this cell has to be sealed, and it cannot be sealed by an ordinary glass plate without this coating. I will explain you why. Say, now of course we will place it inside a cavity. This is your output mirror. For function, we have an output mirror. Now we seal it with an ordinary glass plate. So we have seen that the light that begins its journey from inside will undergo, when you consider the reflection loss on two surfaces, 8% will be reflected and remaining will be transmitted. Now this 8% which is reflected, it will be just lost, this light. And then when it comes back, after it undergoes reflective transmittive loss, from it, again 8% will be reflected, which will be lost. And then it comes here, falls on this. Again 8% will be reflected. And after the reflection comes, again 8% will be reflected. So in a to and fro journey, if you use an ordinary glass plate, 32% of the light which has been generated would simply lost through this reflection. So you can't tolerate such reflective component in your sealing optics, which will seal the two ends of this gas cell. So what you do, you actually seal these two ends with this anti-reflection coated glass plate. This is here. So it would not offer, it would allow transmission of the entire light which is being generated inside. So okay, so we have used that knowledge and we have been able to make a transmittive window, which also is very useful in the operation of a laser. In fact, many lasers, most of the gas lasers, make use of such ARA. Or it is called both sides. You have anti-reflection coating. Now let us go to the next problem. How do you have got anti-reflection coating, that is no reflection, but if you have to make it low transmission window, that means you have to have high reflection. So as I said, we would like to make the transmittive mirror which is 10% transmission and 90%. So how do we do it? So again take this glass plate and we deposit thin film and we again shine. Now, of course, we are taking light of wavelength lambda, this dielectric frame for transmission to this wavelength. Now you are shining it with this light of wavelength lambda. So again, a part will be reflected from this surface, then another, it goes, then from here, again another part will be reflected, most of it will pass through. So this will now again interfere. Now you see, here if you see, what we want, see, for this path difference, it is 100% annihilation. 100% annihilation. And for this path difference, 0 or lambda or 2 lambda, it is 0%. So if we have to make reflectivity 90%, then annihilation should be 10%. So somewhere here. Sorry. 100% annihilation, this is 0. So maybe 90%, 10% annihilation. So we choose a path difference in such a way. This path difference will give you annihilation of the two beams, which is 10%. If 10% annihilation, that means 90% of the beam will be reflected and 10% will be transmitted. See, earlier it was complete annihilation for ARA coated. So there was no energy which was coming out. Everything was going because this was totally. Now we have chosen the path difference in such a way. Suppose the path difference, this path difference is x. This is x. So our thickness of the film now would be 2t equal to x. 2t is the path difference between these two. This is returning from this interface and this is returning from this. So it has traveled this thickness of the film twice. So now 2t, if 2t becomes the x, then this beam would annihilate there will be 10% annihilation. So 90% of the beam light will be reflected. So then 10% will get it. Yeah, this is your glass. And you want that entire 10% should get out. So you put now an anti-reflection coating. So here it is that partially reflective coating, which will give you 90% reflectivity, and here it is anti-reflection coating. So how will you use it in your? You will put this side, that is the partially reflecting side, then glass, and then the anti-reflection. So this is anti-reflection coated. This is glass. And this is partially reflective, partially transmitting. So if you are using it, then 90% of the light will be reflected back into the cavity, and 10% the transmission loss, which will be coupled out of the active layer. It's a useful loss which will form the laser beam. So if you now vary this thickness, and if you can vary this path difference, then you can essentially vary the reflectivity. And in principle, you can choose any reflectivity. However, something that I have not told you is that for this total annihilation, the intensity of the two beams should be same. Then only there will be total annihilation. So, for that to happen, we must choose the refractive index of this dielectric material in such a way that the reflection component that eventually comes out, this and this, the intensity is set. But let us not go into detail. But I think you have got a qualitative picture to how this knowledge that the path difference lying in between the fringe intensity will vary from 0 to maximum. This how you can exploit for the fabrication of the mirrors of laser. However, I must also tell you that in many operations of laser, the even 100% reflective mirror also is fabricated this way. So what you do here, you actually put this dielectric layer, dielectric film, in such a way that there is 0% annihilation, it's a complete reinforcement. So if the path difference, this 2t becomes lambda, then they will completely reinforce. That means the entire energy returns back. Nothing goes in. And because nothing goes in, so you don't need to do anything here. So then, what you will then play this mirror here. This is glass. This is fully reflective coating. So this will offer 100% reflection. So I have tried to give you qualitative explanation, understanding as to how the interference of light property can be exploited to fabricate, manufacture a variety of laser beams. And in fact, the lasers that operate today makes use of this kind of.